Alright, welcome back. Sorry I might have rushed that last video. This feature I'm using only gives me 15 minutes to record the videos in chunks. So, just to recap there, we set our formula up. Sine of 35 over x is equal to sine of 15 over y is equal to sine of 130 over 20. And then we picked our scenarios in terms of cross multiplying. So we got the distance of 6.78 for y, across in the 15-degree angle, and then the airplane is 14.98 miles across from the second tower, or second satellite over here. So what I want you guys to do is go ahead and attempt this problem on your own. I'm looking for find the measure of the angle CBD. So I'm looking for C, B, and D, the whole angle measure up here. And I did give a small hint on trying to get you to look for what you think you need to find first, and that's with the question mark. So we got to make sure we're trying to find certain values first. So I would like you to go ahead and try and see if you can set up a problem to find out what the measure of angle CBD is. You may work with one or two people next to you just to kind of practice the idea. All right, now that you've had some time to think about your scenario, think about your problem, let's just fill in what we do know with this triangle. So we know that we have a measurement of 36 and a measurement of 110, which gives us 34 degrees left over in the triangle up here. And we know that 36 creates this side length BA. So we're going to label that one X, because right now in this triangle ACB, we only have the 110, the 33, the 36, and the 34. So we're missing a side length, and we're missing this side length as well. So we'll go Y. And then you look at triangle BDA, we have 80 degrees, you have 20, but then we don't know these other two angles. We don't know what degree measure that those would be creating. All we do know is that triangle has to equal 180 degrees. Excuse me. So the way we need to go about this is that we need to find this value of x, because that's the overlap between the two triangles. Because 80 doesn't have a side across from it, 20 doesn't have an angle across from it, so we got to create some scenario. So we got to find x first. So I'm going to do sine of 36 over x has to equal, and since we're given these two measurements, we're going to go sine of 110 divided by 33. And we're going to go ahead and cross multiply like we did in the last problem, and we get x is going to equal to 20.64, and I got that by plugging in 33 sine of 36 and dividing that by sine of 110. And that's how I got my x value that is equal to, which is equivalent right here. And then what happens is now that x value has turned into our important information, because now we can get 20.64 is the side length across from 80, so we've now created an angle and a side that match up. So we're given law of sines, we're given an angle, a side, and a side. So we can now go sine of 80 over 20.64 is equal to, and since we're looking for B, since we're trying to find this whole angle, I'm going to find this little one inside first. So we're going to say sine of B divided by 20. So there's a little key reminder here is when you're looking for an angle, what needs to be going through our mind is at some point we need to be taking the inverse sine, also known as arc sine. Basically what we did in chapter 6. On your calculator it's going to be look like this. On Desmos it's going to be arc sine. We're trying to get you guys to be a little bit more familiar with that. So when we cross multiply, we're going to solve for sine of B. We're going to say that this is our unknown, this is our question mark. So that is what we're going to end up trying to find first. So when we do that, we get 20 sine 80 and we divide that by 20.64, and that's where we get the sine of B is going to equal the decimal of 0.9543. And this is important because this tells you that this angle is within the domain restrictions. So a previous from last chapter was -1 less than or equal to 1. This is the domain restrictions in order for you to be able to find an angle. So since this 0.95 falls between these two, we know that this angle exists. It's not an angle we can't have, or an angle that doesn't create a triangle in this case. So when we type the sine inverse of 0.9543, and that's where you're going to get angle B is equal to 72.6 degrees. So to answer our question, what is the angle measure for CBD? We take 34 that we found in this triangle here, and we add it to the angle that we just found in the second triangle. Oops. Fix that, sorry. Got a little trigger happy with my pencil here. We should add 72.6. And when you do that, you get a total of 106.3 degrees. Now, just to keep in mind when you re-look at this to make sure this answer makes sense, you got to keep in mind that that 106 is this whole angle. That's these two pieces that are putting together to kind of form that. So I'm hoping, I know what happened last year, the times we've done this question before, some people are trying to do sine of 36 over 20, but it's only in triangles and it's only the side length that is created. So I hope by now things are starting to click. So let's kind of go into our next problem here. You know, me and the hockey nut that I am, when hockey players attempt a shot, let's say he's 20 feet from the left post of the goal and he's 24 feet from the right post. So he's a little off center. We don't know if he's in the slot or up by the blue line. But if a regulation hockey goal is 6 feet wide, what is the player's shot angle to the nearest degree? So I'm asking really down here, at what angle does he have to get to this bar? What angle does he have to get to this bar? And what range does he have to keep in between in order to make sure that that puck's going to be on net? So right now, if we lose law of sines, we have sine of P over 6 feet, because that's the distance between the posts, which is across from angle P, is equal to sine of A over 24, since it's across from there, so we're going to go 24, is equal to sine of B, which is then 20 feet. So if you notice, like before, every single law of sines problem had at least one angle given. And currently, we don't have an angle that's provided. All we do know is that we are trying to find the measurement for this angle right here. But we're given the three sides. In most cases, this is what happens in real life. You're able to measure from point 1 to point 2, or from A to P and P to B and A to B, but we don't actually know the exact angle. Well, right now, we're stuck. So what happens is when we have law of sines, we can't use it on all triangles. So what happens now is that we're going away from law of sines, and to me, this is the one we're going to use more often, especially when we're able to find set distance, which is called law of cosines. So the next page has got the three formulas on it. I don't want you guys to overlook these formulas. You can memorize 1, 2, and 3 if you choose. For me, I don't just like to memorize one of them. The reason I'm going to say that is because if you know one, you really know them all. Because the only switch is that A has to match up with A. So if I'm looking for angle A, the side length that's across from it needs to be the lead terms. If I'm looking for angle B, or I'm given angle B, then the side length B has to be the one that's by itself. And the same thing here. So these two have to match. Similar to law of sines, where we put the sine over the angle over the side length. Kind of similar scenario. So really, if you just know one formula and just realize that this is the angle given or missing. The side that is across from it will always be the one that's isolated. Now this a squared, b squared, c squared should look very familiar. That's the Pythagorean theorem. Just like here, a squared, c squared, b squared. So it's manipulating the Pythagorean theorem into law of cosines, which is how we're going to show how to derive that, which is coming next. So we're going to show you how what you've done before, what you've used before, how the law of sines was created because we have three side lengths. So here we go. So I kind of set this up a little bit for us. We do know that since this is a right triangle, that x squared plus y squared has to equal a squared. So that's the first thing we do know. Step one, that's from triangle one. Well, the similar process is if we take b minus x. And the reason it's b minus x is because if b is a to c, let's say that's 10 and this is 2, then you know that's 8 because you've taken those and subtracted them. So b minus x squared plus y squared is equal to c. So this squared plus that squared is equal to, this should be a little c, sorry, apologize for that, in triangle 2. So if we take the Pythagorean theorem to find little c, so normally in this case when you're given law of cosines, you're given a side length and a side length and an angle. So we're giving you b, we're giving you a, and we're giving you angle c. So with that said, here's your Pythagorean theorem to find c, and then if I FOIL this out and I expand this b minus x squared out, I get c squared is equal to y squared plus b squared minus 2bx plus x squared. And if you notice here, x squared and y squared, we already found up here, x squared and y squared. So we're going to substitute the x squared and the y squared together with the a squared. So what you found in this triangle, we're going to now take the a squared and substitute. C squared is equal to a squared plus b squared, which is similar to the second formula that we found on the last page. Now, we got to figure out how to get this x, because everything else is expressed in terms of the two side lengths that are given and the angle that's formed between them. So it's a side, angle, side relationship. Well, to get rid of that x, we know how to find x by looking up here. If this angle is given and we want to find x, we know it's the cosine of that angle, or in this case c, is equal to the adjacent over the hypotenuse. And I solve for x. So I'm going to take the a cosine, expand this up a little bit. I'm going to take this value here, I'm going to plug it in for that x, and that gives me b, 2b times a cosine of c, which we cross multiply. That's how we got the x. And now with a little bit of rearranging, just because multiplication can go in any order, we've now came up with the law of cosines formula. So all of the law of cosines formula comes from something we have been doing for a while now with Pythagorean theorem in geometry we talked about, and then we switched it to conics when we did x squared plus y squared is equal to 1, and then we now switched into those identities that we did the last 3-4 days and before break with showing that sine squared plus cosine squared is equal to 1. Well, now all we're doing with law of sines and cosines is we're mixing those trig values together with the Pythagorean theorem to come up with situations where we're able to find any side length, any angle. So when we look at law of cosines, we're only going to be able to do this when it's a side angle side or a side comparison. Because if it's any other relationship, you already have law of sines, and that should be your go-to one. So that's your deriving of how the law of cosines. So what we're going to do next is we're going to revisit this question again, but instead of using the law of sines, we're now going to use the law of cosines.